Most people think uranium is ready to use straight from the ground. They're completely wrong. Natural uranium is almost entirely useless for nuclear power. Only 0.7% of it can actually create energy. That tiny fraction is uranium-235, and without it, nuclear reactors simply won't work. But here's the incredible part. Scientists figured out how to solve this massive problem using machines that spin faster than jet engines. Here's how this breakthrough technology transformed uranium from mining waste into the ultimate energy source. First, let's look at the uranium problem that almost killed nuclear power. In 1932, scientists made a discovery that would change everything about energy, but it also created the biggest problem nuclear power would ever face. James Chadwick found something tiny inside atoms called neutrons. These neutrons could split uranium atoms and release huge amounts of energy. Scientists got excited about this discovery. They thought uranium could power entire cities with just small amounts of fuel. But then they discovered something that almost killed the whole idea. Here's the problem that made scientists want to give up. Natural uranium comes in two types. Uranium-238 makes up about 99.3% of all uranium, while uranium-235 only makes up about 0.7%. That tiny amount of uranium-235 is the only type that can actually create nuclear reactions. Uranium-238 usually absorbs neutrons and doesn't split like uranium-235, so it can't sustain the chain reaction reactors need. Picture this problem another way. Think of trying to power a whole city using 1 grain of sand mixed into a bucket full of rocks. The grain of sand represents uranium-235. The rocks represent uranium-238. The city needs that 1 grain of sand to work, but finding it and separating it from all those rocks seems impossible. That's exactly what early nuclear scientists faced with uranium. This discovery shocked researchers working on nuclear energy. They realized that most uranium was completely worthless for making electricity. Scientists had found an amazing energy source, but almost all of it couldn't be used. This meant nuclear power might never work on a large scale. The Manhattan Project scientists faced this exact challenge during World War II. They needed to separate uranium-235 from uranium-238 to build nuclear weapons and reactors. But these two types of uranium are nearly identical. They're both uranium atoms. The only difference is that uranium-238 has 3 extra neutrons compared to uranium-235. That's an incredibly small difference to detect and use for separation. Think about how hard this separation job really is. Scientists needed to sort atoms that are almost exactly the same. These atoms weigh nearly the same amount. They look the same. They act the same in most chemical reactions. The only difference is those 3 tiny neutrons. Early scientists thought this problem might make nuclear energy impossible to use. The separation process looked too difficult and too expensive. If they couldn't separate enough uranium-235 from uranium-238, nuclear reactors would never produce enough energy to be worth building. The whole nuclear power industry almost died before it even started because of this separation challenge. The stakes kept getting higher as scientists understood the problem better. Commercial reactors typically use fuel enriched to about 3% to 5% uranium-235. That meant processing enormous amounts of natural uranium just to get small amounts of usable fuel. So what makes uranium-235 so special that nuclear reactors can't function without it? When slow neutrons hit a uranium-235 atom, the atom becomes unstable and splits apart immediately. This splitting releases enormous amounts of energy plus 2 or 3 new neutrons. Those new neutrons then hit other uranium-235 atoms, creating a chain reaction that can continue as long as there's enough uranium-235 present. This understanding pushed scientists to develop ingenious methods for separating these nearly identical atoms. The solution would come from studying something completely unexpected that had nothing to do with nuclear physics. Next, the jet engine solution that changed everything. The breakthrough came from an unlikely place: dairy farms. For decades, farmers had used spinning machines to separate cream from milk, since cream is lighter. Scientists saw the same principle could be used to separate uranium atoms. What began as a farm tool evolved into one of the most advanced machines ever built. Engineers designed centrifuges that could spin uranium gas at more than 50,000 revolutions per minute. faster than the spools inside jet engines. And they had to keep spinning at that speed for years without stopping. Any wobble, any vibration could destroy the process and tear the machine apart. The precision required is staggering. Some centrifuge rotors weigh hundreds of pounds. At 50,000 RPM, the forces pulling on them are so extreme that only the strongest materials known to science can withstand the stress. Even microscopic flaws in the metal could trigger catastrophic failure. To enrich uranium, these machines are linked together in vast chains called cascades. Each centrifuge makes a tiny adjustment. One might raise uranium-235 levels from 0.7% to 0.8%, the next to 0.9%. Step by step, across hundreds or thousands of machines, the fuel eventually reaches the 3 to 5% concentration needed for nuclear reactors. This method replaced the old process of gaseous diffusion, which once required facilities the size of cities and enough electricity to rival major metropolitan areas. Modern centrifuge plants achieve the same results with a fraction of the space and power. The transformation inside is remarkable. Natural uranium is 99.3% uranium-238, which is useless as fuel. Centrifuges strip that away, concentrating the rare uranium-235 into a form that can drive chain reactions and generate power for millions. Today's enrichment plants show the scale of this achievement. Some house tens of thousands of centrifuges, lined in rows that stretch for hundreds of yards. Each spins silently, monitored by computer systems tracking speed, temperature, and vibration. If a single unit falters, technicians can replace it without shutting down the entire operation. Chadwick's discovery of the neutron revealed both the problem and the solution. Only uranium-235 could sustain chain reactions, but separating it from uranium-238 required centrifuge technology. That insight made nuclear power practical on a global scale. Beyond Earth, uranium's role in humanity's next frontier. Space missions demand nuclear power in ways that Earth-based systems never encounter. NASA is actively researching small, compact reactors for space missions that could power Mars colonies and lunar bases. Space exploration creates completely new problems for nuclear power that don't exist on Earth. Engineers have to design systems that work in places where there's no air, no water, and temperatures that swing from boiling hot to freezing cold in minutes. Space presents unique challenges that make nuclear power incredibly difficult to use. Without air or water, space reactors must reject heat by radiation, which changes how they're engineered. The extreme radiation in space also damages electronic components much faster than on Earth. Most importantly, space missions need power systems that work perfectly for decades without any repairs or maintenance. Small modular reactors designed for space missions use uranium in completely different ways than regular power plants. These reactors are much smaller but need to be much more reliable. Engineers design them to run automatically without any human operators. The uranium fuel has to be processed to much higher standards because there's no way to fix problems once the mission launches. Even tiny impurities that wouldn't matter on Earth could cause major failures in space. Radioisotope thermoelectric generators represent another way uranium powers space exploration. These devices don't use nuclear chain reactions like regular reactors. Instead, they use the natural heat that comes from radioactive decay. The generators use plutonium-238, which is produced via reactor processing of uranium. This plutonium generates heat for decades as it slowly decays. Special materials convert that heat directly into electricity. The Voyager space probes show how well uranium-powered systems work in space. Both Voyager 1 and Voyager 2 launched over 45 years ago with plutonium-238 power sources. They're still sending signals back to Earth even though they've traveled billions of miles from the sun. Solar panels would have stopped working long ago at those distances, but the uranium-derived power keeps flowing. These probes will keep transmitting for several more years before their power finally runs out. Mars colonies and lunar bases will depend heavily on uranium power because solar energy won't be reliable enough. Mars gets much less sunlight than Earth, and dust storms can block solar panels for months. The Moon has 2-week-long nights where solar power stops completely. Nuclear reactors powered by uranium can generate electricity constantly, regardless of weather or sunlight conditions. This reliable power will be essential for life support systems, manufacturing equipment, and scientific research. Uranium also enables advanced space propulsion systems like ion drives. These engines create thrust by shooting charged particles at extremely high speeds. Ion drives are much more efficient than chemical rockets for long-distance travel, but they need steady electrical power for months or years. Only nuclear power systems can provide that much energy reliably for extended space missions. Chemical fuel would be too heavy, and solar panels become useless in the outer solar system. Space-grade uranium processing requires even higher purity standards than the most advanced Earth-based reactors. Every atom in the fuel has to be perfect because there's no way to service or replace components during space missions. The enrichment process has to remove even more impurities than normal. Quality control testing is far more extensive. Engineers test every batch of space fuel much more thoroughly than fuel for Earth-based power plants. If uranium-based systems can last decades in deep space, what does that mean for Earth-based power? Uranium-powered systems will provide the reliable baseload power that Mars colonies need to manufacture everything from building materials to life support equipment. These same systems will enable spacecraft to travel beyond the solar system by powering ion drives and keeping life support systems running for decades. The manufacturing capabilities that uranium power provides will let humans build sustainable settlements that can grow and expand without depending on supply missions from Earth. From spinning centrifuges to space exploration, uranium has transformed from an almost worthless element into the foundation of humanity's most ambitious energy projects. In conclusion, the technical breakthrough that made this possible changed everything about nuclear energy. Uranium's journey from a nearly useless rock to humanity's most energy-dense fuel represents one of science's greatest problem-solving achievements. Scientists took an element that was 99.3% worthless and figured out how to extract the tiny fraction that could power entire cities. The trick was enrichment, concentrating the 0.7% uranium-235 up to 3% to 5% for reactors, which is what made nuclear power practical. The same thinking that solved uranium's separation challenge can help tackle other seemingly impossible energy problems today. When something looks too difficult to solve, remember how scientists turned uranium's biggest weakness into its greatest strength. This element may play a major role in powering both Earth's clean energy future and humanity's expansion into space. If you enjoyed this breakdown of how spinning machines solved nuclear power's biggest problem, hit that like button.